In a previous video, we talked about how the body can accumulate calcium oxalate crystals and how you could use electrons and high voltage spikes to break those crystals up. Today we're going to talk about another kind of crystal, but these are crystals that form in the body as a result of heavy metal toxicity and what we can do about these. So here's our cell, and the cell likes to be negative on the inside and positive on the outside. And that gives it its charge, its ability to do what it needs to do. Now, metals tend to be positive, and when the cell is negative on the inside, it can pull the metals in, the ones that it needs, calcium, zinc, such and so forth. And then the metabolic wastes it makes are also negative, and since negatives repel, it can push the wastes out. It's a very simple and elegant design. So let's see, what kind of negative things do we have inside the cell? We have sulfates and phosphates, so let's put them in here. And these are normal metabolic waste products of the cell. And what else do we have inside the cell? Well, we have the intercellular metals, that would be mostly potassium and magnesium. And then outside the cell, we have the extracellular, which would be mostly the sodium and the calcium. All right. Now what happens is these cell wastes right here combine with the metals, and they're going to form salts. Now, when you think of salt, you typically think of table salt. That is chloride, which is a negative, and sodium, which is positive, and they make a salt, which together is neutral. But there's lots of salts. Anytime you mix a positive and negative, or an acid and an alkali, you're going to get a salt. Now, there was a Dr. Schussler, in the late 1800s, who analyzed the ash of humans after they'd been cremated, and he found 12 basic salts. And he made an entire healing protocol based on balancing those 12 salts. Now, let's talk about the salts that can happen when we combine these things. Sodium, calcium, potassium, and magnesium can all combine with sulfate and phosphate. And according to Dr. Schussler's research, when sodium combines with sulfate, you get sodium sulfate, and that's good for detox. And sodium combining with phosphate yields sodium phosphate. That helps balance your pH. When calcium bonds to sulfate, that creates connective tissue. And when calcium bonds to phosphate, you get bones. Potassium bonding to sulfate helps with oxygen exchange. Potassium bonding to phosphate is good for the nerves. And finally, magnesium bonding to phosphate is also for the bones. So the way the system is designed, some of the wastes that the cell makes combine with metals, and then they actually become good for you in another way. Now, let's take a look at what happens when you put these things in water. If you put sodium sulfate, sodium phosphate, potassium sulfate, and potassium phosphate in water, they dissolve. They are soluble. On the other hand, calcium sulfate, calcium phosphate, and magnesium phosphate are not soluble. They turn into little crystals. They solidify. And they won't dissolve in water, which is good because we don't want our bones, the magnesium phosphate and the calcium phosphate, dissolving in water. Nor do we want our connective tissue, the calcium sulfate, dissolving in water. So it's a great design. The body uses the ones that aren't soluble to form the permanent structures like the bones, the teeth, and the connective tissue, and the others have jobs where they can move around where they need to. So far, everything's working great. The trouble is, these aren't the only metals in the environment. There are also toxic metals like lead and mercury, and they can make toxic cell salts, like lead sulfate or lead phosphate or mercury sulfate or mercury phosphate. Well, the problem is none of these are soluble. If they were soluble, like, say, sodium sulfate or sodium phosphate, then however toxic they are, you'd let them go in the urine and within a day they're gone. But they're not soluble. They're more like magnesium phosphate or calcium phosphate or calcium sulfate, they don't dissolve in water. And so they stick around, and they're very hard to get rid of. So we're making these. What do we do to get rid of them? Well, first, try not to expose yourself to the toxic metals. But that's tough. We're going to get exposed. So how do we get rid of them? Well, one thing you could do is you could take something like magnesium dipotassium, that means 2 potassiums. So 1 magnesium, 2 potassiums, EDTA. And let's say you take this and it bumps into some lead phosphate as an example. What will happen? Well, the lead is going to attach to the EDTA, forming lead editate. And the magnesium will attach to the phosphate, and the potassium will attach to the phosphate. So you'll get potassium phosphate and magnesium phosphate. Now, the lead editate is soluble. This will dissolve in water. Lead phosphate will not dissolve in water. Lead editate dissolves in water, which means you can now urinate this out. And the potassium phosphate helps the nerves, and the magnesium phosphate goes into the bones. So we can turn a toxic salt, lead phosphate, into a water-soluble toxin that will leave, and 2 nutritional elements. So far, so good. But there's one other challenge. So let's say that this represents our positively charged toxic metal, lead for instance, and this represents our negatively charged phosphate. Well, opposites attract. That's how the lead phosphate formed, right? But if there's another one and another, they'll line up in a grid. Well, this is how a crystal forms. So you could end up with a crystal of lead phosphate. Now, in this graph, the numbers going up here exponentially are solubility, how easily it dissolves into water, and in this direction, its size in terms of nanometers. So what it says is, if something is really, really small, it's very, very soluble. And as it gets bigger, it becomes less soluble. Now, there's a point right about over here. That's about 7 nanometers, which is something like 1/20,000th of a human hair. Once a crystal grows in size to about 7 nanometers, you can see that it's 10,000 times less soluble. So the challenge with these crystals is a lead sulfate, lead phosphate, for example, is still somewhat soluble if it's really, really tiny. And you can use EDTA on it. But once it gets to any size, it's completely insoluble. So how do we deal with these crystals? Well, let me show you some pictures of them. Here are some photographs of different types of crystals. You can see lead combining with sulfate, lead combining with phosphate, mercury combining with sulfate. There's lots of these crystals. They're not going to get that big in our body, but it just shows you how this process forms. Another word about this. Let's say you have 2 magnets and you put them together. Well, they're very hard to separate. So that would be our 2 magnets stuck together. But if you put a bunch of magnets together, the difficulty in separating them goes up much more. So it is far easier to separate 2 magnets of the same size than 4 magnets of the same size. That's what this process is. Crystal formation is like magnets snapping together, and the bigger they get, the stronger they become at this size. So what do we do here? When they're tiny, we can use EDTA, but when they're large, it's going to take a long time. And a lot of the toxic metals are inside this crystal, so the EDTA can't even get to them. So at this point, the idea would be to break this crystal up into individual pieces. So if we can break it into separate pieces that are free floating around, if we could shatter it, now, even though it might be insoluble for the body, EDTA can get to it. How do we crack the crystal? Well, we talked about that in a previous video. We said that if you add electrons, it'll be negative. If you add electrons to in high voltage spikes, you could shatter the crystal. So that's what I think is a good idea. The first thing to do for health is have a good supply of the good metals. Calcium and sodium are easily found. Magnesium and potassium typically you might consider supplementing. And to try to avoid the toxic metals. Consider something like magnesium dipotassium EDTA. Another advantage of magnesium and potassium is they both increase solubility. But still, even with everything that we do, we may still accumulate some crystals. So at that point, you might want to do some high voltage spikes. And what they do is they hit the crystal and they resonate it, and if it explodes into tiny pieces, now in smaller pieces, now that it's here and the solubility is up, what that means is it can go into a water, even something like EDTA is available, and then it can be urinated out. So, if that's something that's interesting to you, we make a magnesium dipotassium EDTA product. There's a picture of it. And if you would like to have the benefit of electrons and high voltage spikes, then there's a picture of the machine we make for that. Have a great day.